We're going to talk about propagation, which is kind of fun. Doesn't require a calculator.
Always good.
Some of the things are what we call moon bounce, or Earth communications. That's one of the things that some amateurs do. I know we have a guy in the NASA club that's done it. It's not a cheap thing to do. Requires a lot of power, about 1,500 watt transmitter, low noise amplifiers, multi-element Yagis, usually more than one gang, because you have a 250 dB loss to the moon and back. That's a lot to make up, and requires a pretty good receiver. The other thing, I'd be interested in trying it, but the meteor scatter, when meteorites come through the atmosphere, they leave a ionized trail, like a little cylinder behind them, and you can basically bounce signals off of those meteor trails. Of course, you only have a minute or two maximum, so I'm not sure exactly how you go about doing it. And you got to have somebody that you can bounce it to, because same with the moon. I mean, you got to have somebody that's listening for your signal. There's some ducting that happens with microwave and I guess UHF, where you can have an inversion layer and actually have the signal bounce in that inversion duct, just like it's doing on the ionosphere itself. You can bounce it off of auroras. We had, what was that, a month ago? We had the big corona event, and you could see the aurora in Georgia. I suspect people were making use of that and bouncing signals all over the place, although it's very erratic because it's not a nice, smooth. If you ever seen pictures of the aurora, they keep changing and all that. And then we'll talk a little bit about polarization. So, if you remember, all radio waves are made up of an electromagnetic and electrostatic field that are going at right angles to one another. And when they propagate or radiate, okay, they go in the direction that's perpendicular to the direction that fields are moving in. In other words, your fields are moving, like if you got a dipole, they're moving back and forth, okay, along the wire and radiating around it. So when the wave leaves the wire, it goes off in the direction perpendicular to that wire. And we say that they're going at a right angle to the oscillating fields. So what are the component fields of an electromagnetic wave, or how are they oriented? Excuse me. In what direction does an electromagnetic wave travel? Come on, it's not hard. No. All right. Which one can you get rid of? Does it depend on the phase angle? No. So that's two of them you get rid of. So it's either Bravo or delta. So does it go parallel to the magnetic field or perpendicular?
Well, I'm confused because it's got electromagnetic wave, and then we're talking about electric and magnetic fields.
Right.
So
An electromagnetic wave is composed of an electric and a magnetic field. You can't really separate them. You always have electric field and a magnetic field.
Okay, so I know one is parallel, it's parallel and something's right angle, but I don't know.
Well, think of it, if it's going to emanate from the wire,
It's gonna be parallel.
No,
No, right angle?
it's going to be perpendicular to the wire, at right angles to the wire.
Okay.
So it would be delta.
The first question said something about the components are at 90 degrees.
Yes.
Well, the components, like you said, that's the electric and the magnetic.
Right.
Okay.
So those are always at 90 degrees, okay, but it's oscillating along the element.
I
Okay.
see, I see.
And when the wave leaves, it goes perpendicular to the element.
Okay.
There's a door should be open. It was open. There was a good video I had, I guess was done by DirecTV, I think, that showed how the waves actually are formed and has to do with acceleration of the field and all this good stuff. But they made me take it out because YouTube banned me because it was copyrighted, so I had to delete it. But it's a very good video. You might hunt for it. It's I think it's called How Antennas Work. Okay. Like I said, we talked about velocity factor and when it's traveling in a medium like a wire. When it's traveling in basically free space, we and it, it's light wavelengths, we call it index of refraction. I guess that's been around longer than velocity factor. So when any electromagnetic wave, and light is an electromagnetic wave, travels through a different medium that has a different index of refraction, just like in a wire or something, it has the different velocity factor has to do with the dielectric and stuff. It causes it to what we call refract or bend. And if you've ever been to the ophthalmologist and they do a refraction test, for $100 to tell you what new lenses you need, all they're doing is determining how much bending they need to do on the light with the lenses. So it's still the ratio of the velocity of light, the speed of light, and the speed in the medium, just like it is when we do it in a transmission line or a wire. Okay, it's that ratio. It's the same deal. They just use a different term. And it will always be, if it's in some medium other than free space or vacuum, should say, it will always be slower than the speed of light. And you remember the speed of light is? Anybody?
300 million.
300 million meters per second. So what determines the speed of electromagnetic waves through a medium? That's it. Okay. Polarization is another one. I don't know. I can't remember if I'm pretty sure they go through polarization in the general. Um, so it's kind of a rehash where we term it vertically polarized if the electric, and we only care about the electric field, even though they're both there. The definition is how the electric field is oriented relative to the Earth. So if the electric field is perpendicular to the Earth, like if you have a vertical antenna and you know your field is moving this way, okay, it's perpendicular to the Earth. If it's like a dipole or long wire, it's horizontal to the Earth. So that's the definition for vertical and horizontal polarized. If it's rotating, which means it's vertical, it's horizontal, it's vertical, that's called circular polarization, which is what you get from a satellite that's rotating because the antenna is actually rotating. So you either need an antenna that you can move around, two crossed antennas to pick it up both ways. What are circularly polarized electromagnetic waves? Oh. Let's see.
Yeah.
Change
D?
your mind?
Could be, yeah, because again, bands, it's not.
No. Right. I guess you can bend the field in the circular shape, but normally the field's
Like phasing the 90 degree antennas, right? That's what I was thinking by bending was
oh,
the phasing, feeding it phase to the other plane.
yeah, it's just simply rotating because, and normally it's from like a satellite, which is rotating.
Right, so we're saying.
I talked a little bit about Earth Moon Bounce or EME. One of the uh, pieces of software that's part of that WSJTX package is one to do Earth Moon Bounce. So it will allow you to detect signals way down, 20, 25 dB below the noise. And you need something like that because of the path loss. I guess people do it because, like I say, it's the ultimate DX. I mean, that's the farthest you can go and get a signal. And you can go up to 12,000 miles if you happen to have coordinate with somebody that's halfway around the Earth. And when the moon is directly and you're both in sight of it, then you could do that bounce and get a 12,000 mile hop. This is just showing kind of a typical one where they went from California to Boston. And this is like a typical antenna that you might need in order to do this. I think I counted about 15 or 16 elements on each of those Yagis, and there are 16 of them.
Pretty sure my HOA.
Yeah, but they're not that big. They're probably doing it at 440 or 23 centimeters.
Still,
Still.
you're swinging a lot of metal there.
So what's the approximate maximum separation measured along the surface of the Earth between two stations communicating by EME?
Yeah.
Okay, apogee and perigee. Perigee is the closest point to the Earth in the elliptical pattern of the moon, and apogee is when it's farthest away. So obviously, your path loss is less at perigee than it is at apogee. So you would try to make a contact if you're going to do this when it was close to perigee. When scheduling EME contacts, which of these conditions will generally result in the least path loss? Does anybody remember MUF? Libration fading. If you're going to do this, one of the other things that makes it complicated is the surface of the moon, if you've seen pictures of it, is not smooth. So you get and it's rotating. So you get this very irregular surface going by. So, the signal is getting dispersed in different directions. And you get these peaks and valleys. What characterizes libration fading of an EME signal? I think they're trying to push moon bounce. I'm thinking about trying it. I did see an article that claimed you could do it on 100 watts, but you got to do it with the digital mode and when the moon is just before it's setting, the right angle and a bunch of stuff. Meteor scatter mentioned, where the meteor leaves an ion trail, small cylinder through the atmosphere, and because it's ionized, you have a bunch of free electrons in it, so you can actually bounce or refract a signal off of it. They're moving pretty fast, and the ions don't last long, so the tail is not that long. So you only have a few seconds or something like that. I think maximum maybe a minute or something. And it works best in the higher frequencies, 28 to 148. So basically the top of the HF band up through VHF. This was thing I found. I don't quite understand their back and forward reflection, but I think what it's trying to show as, depending on where it is relative to you, you get different angles to refract off of it. So you get a different hop distance. So when it's pretty far away, you can see that the angle is much greater than when it's like right overhead. But I don't know why they call that back reflection. It's still. Yeah, but that's not backscatter because it's still forward, the way they show it. Backscatter actually comes back towards you and when a meteor strikes the Earth's atmosphere, a linear ionized region is formed at what region of the ionosphere? Yeah, most of this stuff is in the E layer. Which of the following frequency ranges is most suited for meteor scatter communications? Charlie.
Is that maybe why the 10 and 6 has been so good lately, just because of all the solar activity? Is it maybe the atmosphere is more charged or?
Well, it definitely affects it. I mean, that's what creates the ionosphere.
It seems like 10 and 6. Easily.
Yeah, and we're close to, maybe we are at the peak. We're very close to the peak of the cycle.
I think it's supposed to peak, late spring next year is when it's supposed to actually reach its peak.
Yeah. So take advantage of it.
On that note, last week I wasn't here because I decided to go to the club's QRP gathering. And, I was a few minutes late getting there, so the, landscape was already filled with antennas. I had to go out 100 feet to put my antenna, so I had 100 feet of RG58. That's the only thing I had that long going out to my antenna. And 3 minutes after I got everything set up, it was about just a few minutes past 10 o'clock. Just 3 minutes after I got everything set up and started looking for something to call, I got hungry on 28-430. It was the only contact I got for
Okay, propagation at the higher frequencies can be affected by weather conditions, particularly moisture. I don't know if you've noticed it, like it affects your cell phone. If you're in an area where there's a tremendous amount of people or water, they absorb your cell phone signal. If you're in the forest, it's going to affect it. If it's fog or raining, it affects it. With microwave, and I'm pretty sure UHF also sees this phenomenon. I mentioned the temperature aversions, where you actually call what's called a tropospheric duct. So it's in the troposphere where you have a temperature inversion, and it creates this duct that the signal can actually bounce through, kind of like a waveguide. And you can also see it if there's weather, warm and cold fronts. You can get some refraction off of those fronts. They claim you typically can go 100 to 300 miles with this technique. I can't say I've ever done it. One of the many things yet to do.
You can even hear repeaters that way. So back when repeaters were really active back in the 90s, I remember picking up 676 out of Jacksonville.
Yeah.
Down here, you could hear them clear as day, and you could talk into that repeater all day long. It was just,
Yeah, that's a good five in town though. That's some transition.
there you go. You start hearing the 85 out of there, right?
Yeah, there's one up in around Jacksonville that's on the same frequency as the KSC repeater, and it sometimes interferes.
Sure. Yeah, you start hearing it back and forth. And obviously CTCSS will, at least
Right.
getting into it and hearing it.
There are some websites. One of them is this William Hepburn site. The URL is there, where he posts what they call Hepburn maps, and it's a map showing the density and the probability of this tropospheric propagation. There's a picture of one I pulled down some time ago. It's probably last year's in October. And the different colors, the key isn't shown there, but they tell you the relative densities or probabilities. And he updates that fairly frequently. So atmospheric ducts capable of propagating microwave signals often form over what geographic feature?
That funny word saying Nimbus clouds are a geographic feature.
Well, mountain ranges are.
This is true. The immediately thinking down too.
What is the typical range for tropospheric propagation of microwave signals? Bravo. I talked about Aurora, where you can bounce signals off of the aurora, which is basically the Earth's magnetic field being ionized. And that's what you see is the different colors. I guess CW is the best way to do it. I think it really messes up voice signals because of the fact that it's so irregular and changing, where you might have a much better chance of decoding a CW signal than you do a voice signal. What is most likely to result in auroral propagation? Strange way to ask that question.
Yeah.
I would have thought it was what's most likely to cause it. Well, let's see. So it's geomagnetic storms. It's the sun again. Which of these emission modes is best for auroral propagation? Uh, okay. I'm sure you all know by now that in HF, at least, propagation on the different bands changes from day to night. So some work fine in the daytime, don't work at night, vice versa. Also, the amount of solar activity has an effect where the right amount can charge the upper layers of the ionosphere and make it very good for refraction. Too much, and you get ionization down at the lower levels, and down at the E and F, they tend to absorb the signal. So that's another one of those things. And of course, you know, that solar activity changes from day to night because you're not getting any at night. So that's why the absorption layers at the lower levels basically disappear at night. So you don't get the absorption. So they're talking about the 20, 15, and 10 meter bands work in the afternoon, but at least 15 and 10 don't work too well at night. From what I found, 20 works 24 hours a day, at least now. So when you're trying to, you know, work towards the evening, you can always start switching to one of the lower frequency bands. What should be done to continue a long distance contact when the muff for that path decreases due to darkness? I guess that's a big QSY, right? Go to a different band.
Yeah.
Yeah, it's big.
Okay.